Video stopped. It said, you're out of memory. Oh, I'm out of memory, all right. Yeah, I don't remember anything. I don't even remember my name. Okay? Yeah, but I'm talking about this right out of memory, so I'll pick it up from where I was leaving it off, which is right about this spot here. Pay no attention to that man behind that curtain. And now we have to get the force of repulsion between those two positive particles and see what happens with that. Let's go ahead and plug that into the equation. All right, so Fe equals 9 times 10 to the 9th multiplied by 2 positive and 8 positive. Point here being that if you get a positive and a positive, they repel each other. So, or a negative and negative. If these are two negatives, they would be a negative 10, negative is a positive. So anytime you get a positive answer for force, that means that's a repulsive force. Okay, so let's go ahead and do the math on this. Here we got to add these two together, right? Because we're 3 meters apart, 2 and 1. It's 3 meters, and square that. Okay, so let's do the math. That's going to be 3 times 3 is 9. All right, so that's 9 down here on the bottom. And actually that 9 will cancel out with that 9. See, we don't need no calculator, okay? We're calculators. And then I can go ahead and that's 1. And that's 16. So 2 times 16. So this is going to end up being 16 times 10 to the 9th. Okay, so if I do the math on that, I show you 16 times 10 to the 9th. I'll move it over one spot to make it more official looking for scientific notation. 1.6 times 10 to the 10th. And that's a positive value, meaning a repulsive force here and an attractive force here. Okay, now, the question, remember, was, how much force does this one feel altogether with these two charged particles acting on it? So now I have to use my brain. Now I have to think. All right, you are attracting me, but you are repelling me. You're telling me to get away while this one's saying, no, come to me. Now, these are forces. Forces are vectors, and that means that this attraction that you have on me is being fought by a repulsion that you have on me. So I'm going to try to draw these. Well, look, times 10 to the 10th, 10 to the 10th, same magnitude there. This is 7.2 in 1.6, or around a little bit less than 1/4 of the total. So 7.2 is, a little bit more than 4 times greater than 1.6. So that means this is smaller by about, that amount. So, okay, now what? Well, the reason I did that is this is an attractive force on me. This is pushing me away. Those two vectors are opposite each other. What do we do with vectors that oppose each other? We all remember from way back in the day on vectors that we subtract them. So the overall net total amount of force acting on this particle is going to be 7.2 times 10 to the negative 10th. Oh, I like you. But we have to subtract, oh, I hate you. You, because you're in the opposite direction. So I'm going to subtract this and subtract the 1.6 times 10 to the 10th. Get you out of there. Notice that I'm not going to use the negative for the 7.2. Do not do that. I mentioned that earlier. I said it just shows that there's an attraction. Don't use it in any math that you're going to use the number for. So do not use that negative. It'll screw your math up and you'll get the wrong answer. Okay? So just take the value itself. Take this value itself. It's positive anyways. So take the two values. We subtract them because they oppose each other. One's a pull and one's a push. And if I do that, I will get 7.2 minus 1.6. So what is that? It's 6.2, 6, and then 5.6. So 5.6 times 10 to the 10th newtons overall force acting on this particle. So overall, I have 5.6 times 10 to the 10th newtons acting on this particle due to the other two. The other two have different forces. One's pulling on me and one's pushing me, but the pull wins. The pull is winning. This pulling effect, this is greater than that. So overall, I would still be pulled. I would start to move toward this negative. Now, the interesting thing about that, I think it's interesting anyways, is as I started to move in this direction, the force of attraction becomes greater because the distance is smaller, but so does the force of repulsion. So that's going to constantly change the force of attraction and repulsion. This number here would not stay the same as I begin to move in. It would constantly change. But don't worry about that. We won't get into that. We just want to know, I want you to know, okay, how to calculate the initial overall force on one particle as a result of two others. We could have done the same thing on the particle in the middle. We could have said, let's figure out the force between this particle and this particle, which we already did.